me start. So let me introduce Professor Jan Minár. So he received his PhD from the so LMU is Ludwig
Maximilian
University in Munich. And you started studying spin orbital interaction and its effects on different types of electron microscopies. So then,
it was not yet modern that time.
Okay, so then you moved for a one-year postdoc at a research center in Jülich, and then you returned to Munich as a co-investigator of the project Electronic Structure and Magnetism in Low-Dimensional Systems. Then you got your habilitation in Munich in 2008, and then you stayed there until 2012. You received your habilitation in 2012.
Oh, yeah, right.
Okay, and then you started working as associate professor of theoretical physics and physical chemistry. You have been for 2 years invited professor at it's Sergi. I always forget. It's a university in Paris. Is the Sergi?
Yes. Well, now I think nowadays called Sergi University of Paris. They changed the name, so it's. But it's close to Paris. It's.
Okay, so then in 2019 you received a honorary fellowship at the Munich University, and then since 2017 you have been a full professor at the University of West Bohemia, where you are the leader of the excellence research team, and you have stayed at a number of foreign research institutes like Nijmegen, Jülich, Paris, and in Grenoble, Switzerland, Berkeley, and okay, I guess there's no need for me to explain what your scientific focus is, because probably now everyone here wants to hear from you rather than from me. Okay, again, thank you very much for accepting this invitation. And anyway, so thanks.
Thanks, Marco, for a kind invitation. I'm really happy to be with you today, today morning for me. It's pity that I couldn't come, or the situation is as it is right now. So I hope one day we will meet in person, because these online sessions are not really the thing. So today, as Marco said, I picked up today the topic which might be for you. Some of you quite maybe new, or so I will not concentrate as typically such topics are, where people concentrate on a given material and do some fancy stuff of it. I would like to concentrate today on the photoemission, on the so-called one-step model of photoemission. And more or less the main message of my talk will be to show you that photoemission is not, it's quite a complicated tool actually, and you indeed need several developments to be done in order to understand the measured data. So as Marco said, I'm coming from Plzen. So Plzen, it's in close. It's here in the Czech Republic, close to German border, well, nowadays one has to also say it's not really far also from Ukrainian border, which is very sad what is happening over there. And in particular, me personally, I'm coming from Slovakia, which is over here, and it's really only 170 kilometers from the war. So it's nowadays not really funny. But at least what we have in Plzen, and Plzen is famous for, is this Plzen type of the beer. Probably some of you know. So it's called Pilsner Urquell, which was kind of developed in Plzen, and it's kind of, you know, all over the world sold. But the Plzen has also very strong, it's a quite nice city, which we also, but we have also strong industry there. So there is a Škoda, probably some of you know, it's a car, well, probably you know it from the cars, which is quite a big company for the cars. But in the Plzen, we have the bigger part of Škoda company, which is connected to mechanical engineering, or so building starting from atomic reactors up to trams or big devices. Now we have also a university, and is connected to this industry zone in Plzen. So we have also it's strongly devoted to the applied sciences, and certainly we are much smaller than yours, and we are in the ranking much far away than yours. But definitely, why I'm there is one of the reasons is that typically what I got allowed there to do is to have a department which does both, which on one side does the development of the theoretical tools by means of the multiple scattering formalism, which I will introduce you today. On the other side, that we have a laboratories also, so we do also experimental work, as I said, starting from thin film preparations up to development of some materials for the solar cells and some devices. And that combination is very important, and in the context, I will show you in the context of also on the theory of the developing of the theoretical tools. But me personally, I'm a theorist, and here I just only highlighted a couple of people, and in particular these guys, so Laurent and Fatima Jakub, who were mostly involved in some of the works, which I will then show you and during my talk. So let me start with acknowledgements, just because I will forget. As I said, I spent a lot of time in Munich, and together with Jürgen Braun and Hubert Eber, we were kind of co-developing this SPR KKR DFT package, and from the experimental part today, I will show the results going from the Swiss light source, so from Juraj Krempaski and Hugo Dill, Vladimir Strokov, Claude Money, and some results from the Berlin about the linear dichroism with the Sam Belliot and Ralph Enz. All for maybe those who are doing pump rope or are in the dynamics more or less. If you are researching in dynamics, then Ralph, surely you know, he's quite famous in the time reversal, the time resolved photoemission. So the outline of the talk is quite well kind of a standard, but what I would like to show you at the beginning is just to make a couple of points concerning photoemission, and I will try to also show maybe for students how do we treat the photoemission, how do we calculate it by means of so-called one-step model of photoemission in combination with the multiple scattering technique. And then I have two selected examples. One is a germanium telluride, which is a ferroelectric, interesting ferroelectric material, and surely nowadays very modern 2D material, so tungsten selenide, where I will discuss some dichroism effects. And then depending on the time, either I will stop with one or I will proceed with the two. So let's see. Now, photoemission, it's a quite well-known tool. It's a more or less very unique tool to study the electronic structure of the materials. And the idea is you have a light, you have a photon source, monochromatized light. You shoot it on the surface, and due to the photoelectric effect, you have electrons which are emitted. And what you measure, you can measure the depending now on a combination of the energy of the light and the kinetic energy of your electrons, which you can measure either, for example, you can have a look to the core states. So here is just the example. We did very recently some study on the nickel doped strontium titanate. I don't want to much go into details of this, but it's a kind of interesting material where we have some states close to the Fermi level, which are kind of impurity states, correlated ones. So, but definitely with the core level spectroscopy, core level photoemission, you can access, or the simplest interpretation is so-called chemical shift. And now, depending, for example, on the the oxidation number of your, in this case, titanium. You can have a look. You can see different species, different chemical bonding. Now, when we now go to the valence part, you can look to, and we collect all electrons, or the most of them escaping the sample, or you have a polycrystalline sample. You can measure angle integrated photoemission, where you would have a kind of direct access to the density of states, you could say. So the simplest interpretation is the density of states. Or when we go to the angle resolve mode, that means we also look to the direction, then we have access also to the momentum of the photoelectron. Now you can measure the band structure. I picked up this one, as I said. It's not the most beautiful one, but it is kind of realistic one we did very recently. And the simplest interpretation here, very often you will see, and in any textbook you will say, well, it's a kind of band structure I see, or spectral function. That means imaginary part of the Green's function. What I will like to show you today, in particular in the angle resolved mode, that this is not really always true, such a simple interpretation, and one needs to do more. But as I said, we have also we do also photoemission in Plzen. So if some of you, well, I know it's quite far, but I can promise you that if some of you is doing theory and would like to do also some experiments, we will allow you. So because I'm also a theoretician, also doing some experiments here. So we have a kind of machine, standard angle resolved photoemission machine. In particular, what is special, maybe at least for the Czech Republic, is very special for the region around where we are. We have a spin detector, so we can also perform or measure the spin polarization of the photoelectron. And maybe what is also with the kind of a special, the tools which I will show you today, were actually really very closely with this with the company of Specs and the Focus, were really used to develop this spin detector itself. So we are kind of doing some calculations in order to find the ideal scattering geometry for this case. Now it makes obvious that the people are very happy, but why I'm showing those two is that the Laurent and Sunil are the ones which also contributed later on to the work. So as I said, simple interpretation is not easy, so or not always true. So this is a study we did a couple of within the PhD thesis of Gerald de Rondeau. We did studies for these high temperature superconductors, these iron-based pnictides, where this is just a soft X-ray photoemission data Fermi surface of this potassium doped case. And you see that when you measure it, you will realize that when I go from one gamma bar point to another gamma bar point, you should due to the translation periodicity, you would expect to have the same features here, but you don't have. Now, when you do the simple DFT calculations, just calculate the spectral function here in this case for this material, you will realize that going from gamma to Z, which is corresponding to gamma bar to gamma bar prime, so you will realize that you would expect such a circular, well, pockets here, but you don't. You indeed need a full one-step model of photoemission calculation to realize that, for example, this this propeller-like structure comes due to the surface resonance, which is present. At the X point, you don't see anything here because of the matrix elements effects. So, that means in order to describe such a material, so just note we have a doped system, for example. So we have a potassium here. So we need to have a flexible DFT-based method. In our case, we are using multiple scattering Green's function formalism, so-called Corringa-Rostocker method, KKR. You need to include the correlation effects because these materials are very, well, strongly correlated, so you have to go beyond the standard LDA or GGA functional. So we are using in this case dynamical mean field theory, or you can, as I said, need to include a disorder by, for example, coherent potential approximation in order to be able to do it. On the other side, on the photoemission, there are many effects which you need to include: surface effects, final states effects, matrix elements effects. You need to go to high photon energies in this case, which is also not always trivial. You need to include the temperature effect, so you want to include the lattice vibrations, and so on. So you need to have a kind of combine both tools, and this is actually what we did in the past years in order to be able to describe this. Now, what is a one-step model of photoemission? So, so as I said, first of all, we need to have a method which can where we can describe a given material. We are using, as many others for the solids, the density functional theory. So we are mapping the many electron problem onto the single or on the effective one particle problem. We can go beyond that, for example, by including dynamical mean field theory. And but there are many methods now. You know, the standard way of seeing it, if you have a Kohn-Sham equation and use some variational principle, which is quite a simple technique, you plug in here this basis set, you end up, and now depending on the bases, you end up to the pseudo potential methods. You can end up, so like WASP code or quantum espresso and many others. You can go to localized basis set, so LCO, FPLO method, or you can combine both worlds. You are ending up by so-called augmented methods like LPW, and you need to linearize it. Now, the scattering theory goes completely different road. We are using multiple scattering formalism to solve this equation. We don't use the old scheme which you find in any textbook with respect to the KKR, so wave functions, but we are dealing with the Green's functions from very beginning. And why we do so is that when you most of these variational methods, is you use a kind of certain basis set, or you, for example, very often in augmented method, you linearize your problem. That means your wave function, which is kind of effectively, well, basically depending on the energy, you expand around certain energy which is close to the for example, Fermi level. That means if you would like to use this bunch of methods, for example, to go to very high energies far above Fermi level, which you need for photoemission, then you might have a problems, or you have a problem. So that's why we are using multiple scattering theory. So the idea is here, well, we have a projectile, we have an electron, we are trying to solve the problem. We are throwing it around and looking how it's kind of scattered back, and you can get a certain answer which might be unexpected, but the idea is always you are quite far away. Now, the same concept for some of you probably is certainly known, is used for the X-subs, where you excite, so it's an X-ray absorption technique where you excite the certain core states, and the kind of photoelectron is spreading around the crystal. It's reflected, and depending on the conditions, you get these oscillations, and you can, for example, get the idea about the crystal structure. And that's actually what we do. We end up with a band structure method, as I said, where we calculate the Green's function. We calculate it for a particular energy. We don't need to use a spectral representation for it to calculate it. We really do it explicitly for this energy. And this is the form how it looks like. And the main ingredient is this multiple scattering path operator, which is kind of our main quantity to be calculated. It is a transparent quite to be used. You can use a hierarchy of Dyson equations to for example, to calculate, like here in this case, we did in the past some manganese bismuth selenide, so to calculate such a multi-layer system, or to calculate surfaces, to calculate the add atoms on the surfaces, and so on and so forth. So that's very very challenging and very interesting. But you have to realize that this we do without supercells typically. And we can use this order by so-called coherent potential approximation. We can use the correlation effect. So it's quite a very interesting method. But as I said, the main point is that we can calculate it for mostly for any energy, still within DFT. You have to surely realize that it's still DFT, so we have still the same problems as any other DFT method with the fundamentals of DFT, that we can, DFT is valid for a ground state, but not for excited state. But within these kind of limitations, we can achieve here mostly any energy going from soft to hard X-rays or to very high energies, couple of kilo electron volts if you like, and so on. Now, in order to do the one-step model of photoemission, to calculate it, so we consider the full photoemission process. That means lights come in and the electrons are detected here or emitted. We calculate this within as a one quantum mechanical coherence process. We can calculate it, or we go back typically to the Fermi's golden rule, where we end up with the two main gradients. One is the Green's function of the ground state, and then we have or of the initial state, and then we have a final state, which in our case it's so-called time reversal lead state, which is the best possible single particle approximation for an excited state in the photoemission. And the time reversal lead state means that we have a state which goes into the crystal. It's a kind of plane wave like outside, and it's damped and it goes into the crystals, and we can modulate or simulate like this the particular inelastic mean-free path. This can be generalized. You can go beyond the Fermi's golden rule. You can use a pump-probe photoemission. This we generalize, for example, for this case, well, a couple of years ago. So by using a Keldysh formalism. Now, why it's so well? What is the special about it? It's just a simple Fermi's golden rule. You plug in initial state, final state, and that's it. But you have to consider that this has to be done for a semi-infinite surface. So because photoemission is surface-sensitive technique. And one of the examples here, what we do the calculations for the semi-infinite surface. So if you do the slab calculation here, for example, cobalt and platinum, 38 layers of platinum and 1 layer of cobalt, you will see you have a certain states which are due to the finite slab are appearing, and a certain, for example, hybridizations which are non-realist or not right. So by semi-infinite calculation, we really can reproduce this bulk continuum here, and for example, cobalt states which are now here in red. Now, how we do it? We first solve a single side scattering. So it's like a Lego more or less. This is a nice feature of the KKR. We can first, single side scattering is nothing else as a calculating of the phase shift. Then we combine these into the scattering of the one layer. We combine two layers together into effective scattering properties of kind of two layers. And then we, by so-called layer doubling, we can create it and calculate a semi-infinite surface. It is a similar technique as it's used in the tie binding methods to calculate so-called surface Green's function. So it's that's what we done. And for this, we can calculate then the photocurrent. And as I said, we created a couple of we included a couple of effects into the one package, which is then based on this SPR KKR package, and we include the correlation effects by dynamical mean field theory. I realized that you had a couple of weeks ago Igor DiMarco in your seminar, who was definitely speaking about DMFT probably. And you can include, as I said, Dirac formalism. So all which I will show you before is done on the Dirac, solving the Dirac equation, and so on. So in any case, for those who are interested in, this is a kind of a more or less free package. So you would like to use these features, just let me know and we can discuss it. Okay. So let me come to the first example, and this is this is connected to the most, well, very simple ferroelectric system. This is germanium telluride, and it turned out to have a very, well, non-trivial topology. And it took a while actually to be able to calculate or to measure also the band structure by ARPES of this material. And the idea surely goes back as for example, like because he's always showing this picture where you can now try to manipulate the ferroelectricity, you try to switch by external field, certain effects like Rashba effect, and then you can try to combine it into the device. Now, but why we are going to one-step model? So I will show you the main motivation of this system that time came. The germanium telluride has a very strong. It has a strong Rashba splitting. So we know the Rashba effect, for example, on the surfaces on gold 111. This is just measured in Plzen. So you have a small, relatively small splitting of the states, surface states due to the Rashba, due to the spin-orbit coupling. Now, in the germanium telluride, you find the same thing in bulk states, which is not really very surprising because it is system where it has a broken inversion symmetry, and but the splitting here it's quite huge. And the main idea was, let's try to search for it. We wanted to search for these states and try to manipulate them actually. Now, why they are coming from? As I said, we have a broken inversion symmetry and plus spin-orbit coupling. So without distortion, you see the states are not splitted. With a distortion, that means you have a natrium chloride-like structure, which is then distorted. And you get this splitting. It has a certain spin polarization here shown on the right-hand side, and nice kind of Fermi surface, a constant energy map, if you like here. Maybe it's worth to note that this system internally, so intrinsically, is in the experiment is a p-doped system. So all calculations, which I will show later on, are done for a system where we included the vacancies into the system. Now, let me jump a bit away from the germanium telluride. Now, as I said, we would like to look to the bulk states, and you know very well that the photoemission as such is very surface sensitive technique, and it is surface sensitive technique because of the inelastic mean-free path of the photoelectron. For example, in the standard UV regime, where you do where the kinetic energy is, well, it's 10th of electron volts, you in this inelastic mean-free path kind of universal curve, which is called, you see that we are extremely surface sensitive, and it's quite well-known effect. And the idea is now, for germanium telluride, we need to go to bulk states. So we also you will see the results where we go to the soft X-ray regime, or you can go into hard X-ray regime, where you are becoming more and more kind of bulk sensitive. So your final state then goes kind of more deeper into the crystal. And indeed, as a proof of principle, that was a kind of a technique which we were involved, or I was involved, so the whole decade for this, to develop this technique actually. And one of the first proofs of principle that is indeed you can measure the angle result photoemission at these high energies are this kind of list of papers which are here. But you need also to include the various aspects on the theory side to be able to describe it, like in particular, mostly important thermal vibrations you need to include, and some photon momentum effects. Good. Now, having this, now we can go back to germanium telluride and trying to understand the measured spectra. So let's start with this figure here, where you see when we have a clear surface in the soft X-ray regime, we see a lot of states here in the measured data, when we kept the surface and we realized that those are surface states, and when we kept the surface, we can nicely now recognize these Rashba splitted bands. And as I said, it took actually for years to get this kind of quality of the data. Indeed, this is then true when you now look to this is a surface calculation for the germanium telluride p-doped. You see that you have a surface state which are here, Rashba splitted. You have the red one is a surface resonance, which kind of still goes quite deep into the crystal. And then you have a bulk state which we are actually looking for, and you see it in this zoo of states. You need to find them out. So that was a kind of so we were only able to do that actually to understand the experimental data only once we had these theoretical ones. And indeed, you can now go further and measure spin polarization of these Rashba splitted states. They are very highly spin polarized. So and you can then start to understand many aspects of germanium telluride. And one of the aspects is, which was quite, well, not so surprising, but this germanium telluride is a space group 160. So, and it was predicted by Alexei Soloyanov, who was predicting that for this space group, you should see some special topological signatures where you have three bands which are crossing each other. You have two bands here and one degenerated which is crossing here, and these crossing points are now connected by these nodal lines, and that's have a really special spin texture, and this can only happen with the spin orbit coupling and so on. So it's kind of a topological property, and this is indeed also what we first predicted for this germanium telluride, and then we came to Ura and Hugodil and did the corresponding measurements to search for it, and we found this so-called triple point is between gamma and z direction here. So it's somewhere close to the gamma point, and you nicely find these points here in the going from gamma to z. Or when you now look in a full series of the data, you will find it is somewhere here. And now the first step is also to find it in the experiment. And just as a side remark, it is not only this triple point. So the germanium telluride turned out to have a really kind of full zoo of the topological special properties. There is a wild point. So there is a wild point here. There is a kind of Dirac point here with a special spin textures and so on. Okay, so one of the ways now we need to go indeed, and this is what the soft X-ray photoemission can do very nicely, is to find this point here, is to change the photon energy, and by changing the photon energy, you are kind of going through the Brillouin zone. You can go from gamma to z, and you can try to find where we are or what we need, where we need to go actually to find this state. And then once you found it, you can now go back to the energies which have a quite better resolution typically. And so the UV regime, where indeed at about 30.5 EV, you can nicely find this state. You can then start to analyze it. It has a certain spin texture. It's already very difficult to plot it nice arrows, because it's already in 3D dimensions, so it's but one can analyze also some spin texture and spin widening around this point. But definitely what I wanted to show here is that indeed you need it. This study wouldn't be possible without the theory, I would say. Now, the one of the directions where we go also on the theory side, actually, but also on the experimental side, is to be able to do the experiments, ARPES experiments, on operando conditions. That means, for example, to do it at the ambient pressure. So there is so-called ambient pressure XPS. or you can try to do it under the electric field. And one of the first actually measurements on this kind of conditions was at least to my knowledge, was done by us, where we wanted to look to modify to have a germanium telluride here, and this this green on the indium phosphide substrate, and we wanted to switch this Rashba splitted surface. Then we wanted to switch it. We wanted to switch the electricity and manipulate to manipulate the spin texture. And in this was done in this special device, which was then created. We put it here, electric field, and did ARPES measurements. Certainly the quality is not anymore so nice. So what is happening is that you have here germanium in the structure, and you can go back and forth. You can try to switch it back and forth, so to ferroelectrically to switch the polarization and to switch it. But what it turned out is actually when we switch this back and forth. So let me come here. So when we now switch, forget about, there are different points which are measured. Sorry for a busy slide, but let's come to the one. So what will happen is when we put the 0 voltage as ground, we have a polarization along this direction, and we can switch it indeed here. We have a spin polarization along this direction. But then when we go several cycles, you will realize that it's kind of stuck somewhere in, so it's not kind of reproducible. So it kind of stacks in a certain state. You have to anneal the surface again, and then you can start the cycle again. And what is happening is, again, the theory could help us now here, where we did calculations for this germanium telluride, and the surface of germanium telluride wants to be always tellurium terminated. This is kind of the ground state of the surface. And when you start to switch, the tellurium, so germanium atoms up and down, so when you try to switch the bulk, you will realize, because the surface is spined, you end up with some domain wall here in between, which is so without the polarization. So it's kind of natrium chloride-like domain wall. And you can't switch it anymore. So you are stacked over there. So this is a kind of bad news for the germanium telluride, but the good news was that we were able to do it. And indeed, now also on the theory side, now we are using the non-equilibrium Green's function technique now to be able to do the photoemission calculations under the bias. So when there are first steps done, but it's still not in such a shape that I can show it to you. Okay. The next example is a bit more goes direction to show you that more or less, well, we found a nice way how to kind of make use of a polarization of the light. This is certainly not new, but the way how it's now analyzed, it's new. And we applied it to the transition metal dichalcogenides, which are certainly beautiful materials. There is a lot of physics around. And as I said, also on the side of photoemission, there are effects very closely connected to these materials. So you know it very well. Those are kind of 2D materials where depending now on the elements you have in, you can have a semiconductor, semi-metal, you can tune the properties. There are beautiful effects appearing here, new effects like twisted layers with a new kind of quasi-particles appearing, superconductivity, and many huge amount. So it's I think nowadays everybody's playing with these guys. Now, what we took a tungsten selenide, and we took it because it is as if you take only one layer, it has a broken inversion. If you go to the full material, then it is recovered. And this broken inversion symmetry leads to the interesting effects. And so-called hidden spin polarization. Now, the measurement was done here on using a new type of detectors. So Gert Schönhenser developed a beautiful device where you can measure at the same time, you can measure the full band structure of the material. This is really kind of new aspect. And this is very important aspect in our study as well. Now, you surely know very well that the orbital character of the bands doesn't matter if you have a trivial case or you have a topological insulator. The orbital character of the bands plays a big role, and you would like really also to get a really direct access to the orbital character of these bands. Now, all this is true also for tungsten selenide, where you have here in the band structure, when you go to K and K prime point, you have a special hidden, so-called hidden spin texture, which is you have a spin polarization of these the states. You can nicely measure it. You can see that the DFT is really beautifully reproducing it. So the correlation effects here are not so strong. So you can nicely reproduce it. So on the right-hand side is the one-step model photoemission calculation, and the left-hand side the experiment. So, but these K and K prime point are inequivalent. And what it was certainly shown that when you look to them, they have a D character, and they have a certain spin direction, and the D character is then a mixture of dz squared plus this mixture of those two orbitals here with some I phase here. Now you can measure the spin polarization of it very easily, more or less easily. Well, you can get it by angle resolved photoemission, as this beautiful work nicely showed it. But what about to get access to this, for example, to this D character, or to this hidden kind of mixture here, because this also comes into the play due to this kind of hidden character of this band. So what is the orbital texture of this? The linear dichroism in the photoemission is very well known technique. So what you do, you shoot the linearly polarized light, and now depending on the orbital on the polarization of the light and on the character of the bands here, you can get access to the polarization. So you can access, for example, with the white polarization for molybdenum telluride, you can access to the certain orbitals of and get information about it. But the problem is here, linear dichroism in the angle resolved photoemission is that the light breaks the symmetry, and the geometry of the experiment plays a crucial role to understand actually these effects. And our idea was, now we wanted to make use of this new type of detector plus the theory on the top of it to understand the orbital character. So what you can do is, now when you have our bands here, as I said, they have a certain orbital character with this I phase here and the spin. And we know when we go from K prime point to K point, what is happening is that you kind of apply time reversal operator. Now, when you can switch, then you switch here the spin, and you switch this phase, which is here hidden in this after this plus minus. Now, how to do it in the lab or the experiment, also in the theory, is just to rotate the crystal by 60 degrees, and you get this. Now, you can now, having this aspect means that you can now access, so you can, having measured everything at the same time, plus linear polarization, you can get rid of these geometry aspects, and you can now access a new type of dichroism, which we call time reversal dichroism, which indeed can be nicely now seen here. This is an experiment at a certain binding energies, the corresponding theory. So again, very beautiful agreement between also for the dichroism. And actually what you now get is the information about this orbital character, this change in the phase of the orbitals. You can see it in such a way that it is hidden because if you do atom layer calculations, so you see that the main character of the band or the main dichroism effect here. So on the left-hand side is the bulk measurement. On the right-hand side is only one monolayer. So you see we can reproduce it already in one monolayer, this effect. So it is kind of the effect of this dichroism comes indeed from the first layer. And the second thing is when you now modify the spin-orbit coupling, for example, going from fully relativistic to the non-relativistic case by scaling for example, the speed of the light, you will realize that you still see this, blue-red linear dichroism, it stays, and also in the non-relativistic limit. So it has to do not with the spin polarization, but it is really connected to this orbital character. And this can be then used. We used it for different other materials. We proved it also by some tie binding calculations and so on. So the conclusion is that indeed with this kind of new type of dichroism, you can now really access this kind of texture which you see here. It's clear texture of this orbital character of these bands. Now, but I wanted to show you as a take-home message, my last slide is to show you that one has to be careful with the ARPES. So there is a really very strong movement now in the community, actually, in the photoemission, but also there are many theory papers nowadays showing that when you use a circularly polarized light and do certain, and measure the circular dichroism, which is done here. So this is just the same story as before, but you use the circularly polarized light. So you subtract the right and left polarized light, you get a certain texture. And people already in the past said, for example, for topological insulators, that this is connected to the spin texture. We showed it that it's not true. It is connected to spin and orbital and many other aspects. For example, for bismuth selenide and telluride. Now, in this case, what people started to say is that this dichroism should be connected to the Berry curvature. And what I want to show you that is not also true so easy, because when you just simply change the photon energy, that means your final state, you get a reverse of this dichroism. So you get from blue red, you get you see the strong change in this dichroism. So you get it really very well things. That means the take-home message is here also, even though in your Fermi's golden rule, it's very easy to add the free electron-like final state in the tie binding model, for example, it's very easy, you can do it. And you can try to, you get the beautiful results, and which are formally right on the paper, but this approximation of the free electron-like final state in photoemission is quite bad approximation. One has to be careful. So thanks for your attention. And just to summarize, so I showed you that this one-step model of photoemission, and actually many developments we did in the past of the technique on the theory side can now allows you to describe many aspects of the photoemission phenomena. And I also wanted to show you that one has to be careful with interpreting the ARPES data. Not every line you see in the ARPES data can be band, or it is your band. So there are different aspects, and if this you believe me, then I will be happy to to show that to you. So thanks for your attention, and I'm happy to answer all questions.
Thank you, Jan, for the very nice talk. So are there questions? Okay, maybe I can. Okay, I wanted to ask you first a very short question, and maybe I've already asked you. What kind of spin detector do you have for your ARPES?
So let me come back. So I don't have a slide on that, but at least it is.
Is that a Mott detector?
No. Well, sorry. Yeah. So it's over here. You know that kind of, you could say, indeed two types of detectors. So you make use of scattering, and either you make use of scattering on the spin orbit coupling material, so like gold. Then it's a Mott detector that your electron, depending on the spin, will be scattered to the left or to the right. Or you can make use of exchange splitting of the band. So you have a magnetized thin film. In our case, it's a iron oxide thin film. And then depending on the direction of the applied magnetic field, which you can do here from this point here, you can measure the given component. And in this case, we can measure all three components, so X, Y, and Z.
Okay, perfect. And if I remember correctly, this one takes, how to say, much shorter. So, because if I remember correctly, the Mott detector has a very relatively weak sensitivity. So you need to, how to say, keep measuring for a long time. So this one should be
more problem is, well, this is well, that's true, it has a bit higher sensitivity, but the main problem with the Mott like style detector, and you know, depending on the material you use, sometimes was used tungsten, for example, then you have to very often to because it's a, well, you need very often to clean the surface. And now it is, as this is now iron oxide, so it is already oxidized, so you can clean it once per couple of months and you keep it and you can do the measurement. But both is true. One is the practical aspect, and the second one, and the other difference is that in this case you use low energy diffraction, so you have a kinetic energy of a couple of electron volts, and in the Mott you go really to very high voltage, so kilo electron volts, and this is certainly much easier than to handle also in the lab to have a low voltage here.
okay. Thanks. And so I have another question. So you mentioned that so you can do also time resolved ARPES.
Yeah.
So what are the effects that you can include? So because I suppose you cannot, how to say, calculate all time evolution of excited states. So what is it that you can include?
So there are two ways of doing it. Some couple of papers or couple of works we had, and we're still working on that, is to use, you know, to make a use of the fact that when you do this, well, when you are in the femtosecond regime and you then very fast kind of you have a thermalized system, and then you can use the same formalism here to describe many aspects of the photoemission. Yeah, so that means you really calculate it from the ground state. That's one point. But you can do it also with this Keldysh like formalism with the G lesser. So really two times. So the Green's function, which depends on the two times. And nowadays we do it, or well, I wasn't involved in this work here, but later on Jürgen Braun did further developments. So we do it with the approximation, then the pump pulse it's weak, so it is kind of a 2 pp, 2 photon energy, 2 photon electron photon energy, 2 pp photoemission. Let's mix this, and where you solve kind of Dyson equation, you know, and then you do kind of Born approximation to it. That means that kind can be done, and this was done. It was done for example for Rydberg states and so on, and now we are working to have a full-time evolution. And now certainly now it's the question how you describe your which Green's function you plug in, that, or let's say that way. And one way what we do, what can be done now, and it's turned out to be more practical, is to use a TDDFT result. So you kind of, for your initial state, if you like, you use a TDDFT or the propagation in the time, and then apply the formalism to calculate the photoemission step on top of it. You surely need to make approximations, and the main problem here is indeed you have a Green's function which depends on the 2 times, and you have to keep all time evolution of it. So you need a huge memory. Really, in the computer, you need a huge memory to do it. So, yeah.
Okay, thanks. Other questions? Okay. Okay, then I would say, yeah, because already we've been discussing quite a few times with Jan, so probably. Okay. Anyway, guys. So I would say then if there are no other questions, so then I can thank Jan again for this very interesting talk. And okay, so I would say then we can close this session.
Thanks for coming.
Okay, thanks. Okay, yeah. Okay, Jan. Well, I guess then we can discuss other times.
Yeah, well, I have morning, so or maybe we can stay and we discuss further.
Sure. We can actually stay, or maybe I can send you another Zoom link and then we can discuss.